Hello everyone, welcome to today's lesson on the extraction of metals. It is our fourth lesson in Unit 3, Chemistry in Society. So today we are going to be looking at the different ways that metals can be extracted from their ores. You will know you have been successful if you can explain why most metals are found as ores, if you can describe the different methods of extracting metals from ores, and explain why different methods are used to extract different metals. Now, before we go on, as agreed last time, so before we move on to that, what I'm going to do is I am going to go over the white workbook pages on oxidation and reduction. So page 55, I asked you guys to do last time, I'm going to go over that now. So, you are asked in question 1. Which of the following statements is correct? Reduction is a loss of electrons. Oxidation is a gain of protons. Oxidation is a loss of electrons. Reduction is a loss of protons. So first of all, you can eliminate B and you can eliminate D. The reason for this is oxidation and reduction is all to do with the loss and gain of electrons. That leaves you with A, reduction is a loss of electrons, and C, oxidation is a loss of electrons. If you're not sure, we remember oil rig, oxidation is loss of electrons, and reduction is gain. So that leaves us then with C, oxidation is a loss of electrons. Question 2. In a redox reaction, aluminium atoms are oxidised to aluminium 3 plus ions. So write a balanced ion-electron equation to show this reaction. You may use the data on pages 99 to 100. Now, you don't need to use that, you should have a data booklet. So you should see from your data booklet that our aluminium ions that we start with are Al, they become Al 3 plus ions, and in the process of doing so, they lose 3 electrons. The other ion-electron equation in the reaction is Cu2 plus 2 electrons becomes Cus. Write a full redox equation for the overall reaction, and again you should be using your data booklet to help you. So we've got to combine this oxidation here and our reduction reaction here. So aluminium is oxidised to aluminium ions and copper ions are reduced to copper atoms. Now in an ion-electron equation, we have to eliminate the electrons, we have to cancel them out. So we have 3 for our oxidation reaction and 2 for our reduction. What we have to do is we have to multiply everything in this reaction by 2. So we have 2 aluminium 3 plus, and 6 electrons. We have to take this equation and multiply it by 3. So we have 3 copper ions, 6 electrons, and 3 copper atoms. We can then get rid of our electrons, and the whole equation written out looks like this. 2 aluminium plus 3 copper 2 plus ions gives 2 Al 3 plus 3 copper atoms. So, next question. The full redox equation below shows a redox reaction involving hydrogen ions and zinc. Write the balanced ion-electron equations to show how electrons are transferred in the reaction. So for the zinc equation, let's look at zinc. So zinc is here. We are starting with zinc atoms, and we are going to zinc 2 plus ions. Now, zinc is a metal, and to form a 2 plus ion, it's got to lose electrons. So it's going to be oxidized. Oxidation is loss of electrons. Those electrons are on the right hand side of our equation. For a hydrogen ion electron equation, we start with, Miss McVerton hold our pen properly, 2H plus ions and they become H2 gas. So in order to form hydrogen atoms, there has got to be a gain of electrons. So in this case, we will add our electrons on this side of the equation. This is a reduction reaction. So state the element that was oxidized in the reaction. The element that was oxidized is just zinc. So check through your answers if you haven't already. If you have any questions about where my answers came from, or you're not quite sure where you went wrong, send me an email, let me know you're struggling, and I'll do my best to help you out. So let's move on to today's lesson on extraction of metals. So ores are naturally occurring compounds of metals. So metals are very rarely found uncombined on their own in the Earth's crust. Only the less reactive ones are found as pure metals. The most reactive ones need to be extracted from ores. The extraction of a metal from its ore is an example of a reduction. So when we take a metal out of its ore, we reduce metal ions to form metal atoms. Some metals can be obtained from their metal oxides by heat alone. So you can take some metal ores, heat them up, and you're able to extract the metal. Some need to be heated alongside carbon or other substances like carbon monoxide or hydrogen, and some need other methods. The more reactive the metal, the stronger the method required to remove it from its ore. So the more reactive metal, the higher up that electrochemical series that metal is, the harder it is to get it out of its compound, the more energy is needed to extract it from its ore. From the balanced equation for the extraction of metals, the reducing agent can be identified. Now, the reducing agent is what causes the metal ions to be reduced to metal atoms, and we'll talk more about that later. So, here's what you should already know before going into this lesson. Metals are natural resources, which means they are found in the Earth's crust. Few metals are found as the native metal in nature, which means you just find it as a pure metal. This means that metal is found as an element, not in a compound. Now, these metals are your least reactive ones, things like gold, silver, copper. Most metals, though, are more reactive, and they instead are found as compounds, and these compounds are called metal ores. So here is an example of some metal ores. We have iron pyrites, which are a lovely gold colour. We have lead ore, which is silvery, called galena. And we have a list here of different metals and the ores they are found in. Some metals only have one ore, others have multiple different ores such as copper and iron. So how do we take metals from those compounds? So most metal compounds are found in nature are oxides or sulfides. So those ores are either metals in a compound with oxygen or with sulfur. So what is actually happening to the metal when we extract from the compounds? So let's take silver oxide for example. Silver oxide is extracted or broken down to form silver and oxygen. We take the compound and we split it into the two elements that make it up. So as a balanced equation, that is 2Ag2O goes to 4 silver and 1 oxygen molecule. So let's take a closer look at what is actually happening to the silver. So we're going to split this into its ionic formula. So we're going to show it, this is its chemical formula, we will show it as its ionic formula. So silver oxide is actually made up of 2 silver ions and 1 oxygen ion or oxide ion. So let's take silver on its own. Let's forget about oxygen just now and the oxide ion and look at what's happening specifically to silver. So the silver ion is becoming a silver atom. Is this oxidation or is this reduction? What do you think? Silver ions are gaining electrons to form silver atoms, therefore this is a reduction. So the extraction of metals from their ores is an example of a reduction reaction. The more reactive the metal, the more energy is required to extract it from its ore. I've already said that today. The most unreactive metals only need heat to be extracted from ores. Those would be silver, mercury and copper. Now the bonds that they form with the oxygen or silver they are in a compound with are the weakest bonds, which means they only need heat to be broken. Now more reactive metals are extracted using heat and something else, such as carbon, carbon monoxide or hydrogen. These have stronger bonds between metal and either oxygen or sulfur, which means they need a little bit of a helping hand to break the bonds. And the helping hand comes from the carbon, carbon monoxide or hydrogen. Metals that are extracted in this way are things like lead, iron and zinc. The most reactive compounds require electrical energy to extract them from their compounds. And that electrical energy is called electrolysis. We need the electrical energy because the bonds formed between the metal and the sulfur or oxygen in the ore are the strongest bonds. And we need to break those, and to break those we need electricity. Anything from aluminium and above on your electrochemical series will need to be extracted from its ore using electricity. So, how do we do it? This, in case you are unfamiliar, is the reactivity series. As we move from platinum all the way up to potassium, they become increasingly reactive. So platinum would be your least reactive, potassium your most. Aluminium, magnesium, calcium, sodium, potassium, everything above carbon, because they are so reactive, are extracted by electrolysis. Zinc down to copper, metals below carbon, are extracted by heating them alongside carbon in a blast furnace. We're going to look at that in a bit more detail in a second. Silver, gold and platinum have very low reactivity. They won't need to be extracted because they're so unreactive. You'll just find them on their own. They will not be in a metal oxide. So, let's look at each of the methods we've talked about in a bit more detail. Let's start with using heat alone. So, this will only work for silver oxide and mercury oxide. So, Silver oxide is split into silver and oxygen. As we've seen before, our silver ions are reduced to form silver atoms. How do you think the same equation for mercury 2 oxide is going to look? Well, it's going to look a bit like this. So mercury oxide is split into mercury and oxygen. So our chemical equation for that, our balanced chemical equation, is 2HgO gives 2Hg plus O2. What we would then do is we would take our mercury oxide as an ionic compound and use its ionic formula, which is Hg2 plus O2 minus. We would then focus purely on the metal again. This time it's mercury. Like the silver, it is being reduced. So Hg2 plus 2 electrons becomes 2 Hg, and it would be liquid because mercury is our liquid metal. So, extracting metals using heat and another substance. So for metals above copper in the reactivity series, we need another substance along with heat to extract the metal from its compound. The substances used are carbon, carbon monoxide and hydrogen. Examples include the extraction of lead from lead oxide. We use carbon, so lead oxide plus carbon will give you lead and carbon dioxide. We can do the same. We can extract iron from iron oxide using carbon monoxide. That will give us iron on its own and carbon dioxide. Tin oxide, if we heat that with hydrogen, we will get tin and water. So in each case, your metal is always reduced and the other substance is oxidised. So your carbon, carbon monoxide and hydrogen are being oxidised and your metal is being reduced. If you don't believe me, I will demonstrate now. Lead ions gain electrons to form lead atoms. The same goes for our iron ions in our second example. They gain electrons to form iron atoms. And third and final, tin ions gain electrons to form tin atoms. So in each case, as I've just demonstrated, your metal is reduced. Now the other substance, carbon, carbon monoxide and hydrogen, they are all on a dip. So in each case, as we said, your metal is reduced, it gains electrons. Your other substance, carbon, carbon monoxide or hydrogen, would be oxidised. Now these other substances are known as reducing agents. The presence of a reducing agent will cause your metal to be reduced. Let's have a look at the extraction of iron, since iron is one of the most commonly used metals. It's often found in ores as iron oxide, and the iron is extracted from its oxide on a large scale in a blast furnace. Now, because it's one of the most commonly used metals, we have to extract it on an industrial scale, and we do that using this blast furnace. So, here is your blast furnace. Hematite, which is iron ore, is added in at the top with limestone, calcium carbonate and coke, carbon. They're all fed in at the top. Hot air is blasted in at the bottom. And in the middle, carbon reacts with oxygen from the air to form carbon dioxide. The carbon dioxide reacts with more carbon to form carbon monoxide. The carbon monoxide is our reducing agent. It reduces iron oxide to iron, and the molten iron is tapped off down here. So the equation for this, or the word equation for this rather, is iron oxide plus carbon monoxide gives iron plus carbon dioxide. Your molten slag or waste is tapped off here. So iron goes from the bottom, taken off to be used, and slag or waste is tapped off here. Okay, so what you should now be doing is you should complete your blast furnace sheet for your notes. So that takes us to our most reactive metals. Now the metals at the very top of your reactivity series form very strong bonds in their compounds, and because of that they can't be removed from their ores just by using heat and another substance. We need much more energy to break the bonds, and that type of energy is electricity. Now when we break up a compound using electricity, that's called electrolysis. The compound to be separated must be molten or in a solution before it can be electrolysed. So you can't just take an ore in its solid form, looks a bit like a shiny rock, and electrolise it. You've got to melt it down or have it in solution before you can separate the elements using electricity. We use carbon electrodes because they're unreactive. They won't react with your metal or your non-metal ions produced. And this is what the setup looks like. So we have our molten or in solution compound here. We have two electrodes, one positive, one negative, connected to a battery pack or an electricity source. In the lab it would be a battery pack. So we have a positive electrode and a negative electrode. In this example we have a solution containing copper and chloride ions. So we've got copper chloride solution here. So we can see we've got a mixture of copper 2 ions and chloride negative ions. When the electricity is turned on, the copper ions, which are positive, are attracted to the negative electrode, and the chloride ions, which are negative, are attracted to the positive electrode. When we electrolyse copper chloride, negative chloride ions move to the positive electrode and the positive copper ions move to the negative electrode. It is important to remember that in electrolysis our opposites attract. So non-metal negative ions go to your positive electrode, and metal positive ions will go to your negative electrode. In an ionic solution, the ions are free to move, and so they can move towards the oppositely charged electrode as they're not trapped in the lattice structure. Positive ions move towards your negative electrode, negative electrons. Positive ions move towards your negative electrode, and negative ions move towards the positive electrode. So, let's have a look at what's happening here. At the positive electrode, you have chloride ions becoming chlorine gas. They are being oxidised. They are losing electrons. At the negative electrode, you would see a rust-coloured compound forming over the top of the grey electrodes. And what is happening is copper is accepting electrons, is gaining electrons, and those ions are becoming copper atoms. So there's a reduction happening at the negative electrode. And our overall redox equation for the electrolysis of copper chloride is 2Cl- plus copper 2 positive gives chlorine gas and copper metal. What you should do now to summarise this lesson is you should complete your extracting metals summary by filling in the blank spaces. You can then move on to this reactivity of metals summary, because now that we've covered reduction, oxidation, redox, reactivity of metals, extraction of metals, you should be able to answer all the questions on this sheet. And there is also the small matter of our white book, page 54, to complete. It's a short exercise, it shouldn't take you too long. So, our intention today was to discover the different methods of which we can extract. So our learning intention today was to discover the different ways metals can be extracted from their ores. Hopefully you can now explain why most metals are found as ores, describe the 3 different methods of extracting metals from ores, and explain why you would use different methods for different metals. As always, please get in touch if you have any questions or you need something to be explained over again. That's totally fine. If you're happy with the content covered, please have a go at the different activities that we've looked at on our way through to make sure that you get the most out of the lesson. Thank you for tuning in, guys. I will see you all soon. Bye.